Okay, so welcome back, everyone. Uh, did the lab session go well last week? Are there any questions about it? Or okay, good. So we can go back to chapter 4 and part 3. So the first chapter of part 3, which was about machine learning for non-parametric models. So I'm just going to summarize what we discussed last time, which was about what non-parametric models are. So suppose you want to predict a variable y from x, from some covariance x. So your y could be, in the example, the log of price of a housing unit. And x could be the number of square meters, the year of the building, the EPC label, etc. So one way to do that we already discussed in part 2 is just to run a linear regression to predict y from x linearly. Okay, so you just find the best fitting line from y to x. However, what I think should be clear to you is if you had an extremely large dataset, a better predictor of y given x would just be the conditional average of y given x. So the conditional average of y given x is just the average value of y across observations which have a given value of x. Okay, so if you want to know what is the price of your flat, what would be the price of your flat if we were to try to sell it, and your flat is 100 square meters, EPCB, and built in 1990, then probably the best prediction would be the average price of flats which have exactly the same characteristic. Is that clear for everyone? Or not? That would be, in an ideal world, that would be the best prediction if you had a lot of data. Is that clear, or is there anybody who disagrees with this statement? Okay. Now the problem, of course, is that in a typical data set, you will have very few flats which have exactly these characteristics or have characteristics which are close to the ones of your own flat, right? Like if you have a data set of 100 flats in Leuven at random, there will probably be very few which have at the same time 100 square meters, EPCB, and built in 1990. Okay, so that's why people sometimes prefer to go for a linear regression, because we don't have enough data to estimate the conditional expectation, this object. So in practice, you have kind of a tension between, if you want to do prediction, you could say, I just go for the best linear predictor for estimating the best fitting line. This best fitting line, if you were to know it, would be a worse predictor than conditional average, but it's much more easier to estimate in practice. So this is the tension. The tension is you can either decide to estimate an object which is a worse predictor but easier to estimate, or to estimate an object which is a much better prediction but harder to estimate. And so this tension you can also find in terms of statistical models. So in statistics, we have different kind of models that we can impose on the data. We can start from parametric models, which are the least flexible type of models. They are easier to estimate, but they may not be representative of all type of data. And if you use them for prediction, they may not be ideal for prediction. And you can go to non-parametric models, which are the most flexible. So essentially, that's what underpins the conditional expectation. but are much harder to estimate in practice. Okay, is there any question on this so far? Is that clear for everyone, this tension between having a simple object to estimate which is less useful, or a more complex object to estimate which is more useful? Okay, so let's go for examples of parametric, semi-parametric, and non-parametric models. So in statistics, we say that we have a parametric model where the distribution of the data depends on a finite dimensional parameter theta, so meaning it depends just on a finite set of real numbers. So one example is just the linear model with Gaussian noise. So if you assume that y is x prime beta plus epsilon, where epsilon given x is always a normal 0 sigma square, then all the distribution of y given x depends just on beta and sigma square, because in that case the distribution of y given x is just x prime beta, a normal x prime beta sigma square. So it depends fully, if you fix x, the distribution of y depends fully on beta and sigma square, and these are real numbers. Okay, so that's why we call that a parametric model. Like, you constrain the data to the distribution of the data to depend only on real numbers. It cannot depend on functions, it depends on real numbers. Another example is the probit model. Here you say that y is equal to 1 if x prime beta plus epsilon is greater than 0, and 0 otherwise, and epsilon given x follows a normal 0-1 distribution. In that case, the distribution of y, meaning its probability to be 1 or 0, is fully determined by beta once you have fixed x. Do you agree with that? You fix x, and then the distribution of y is fully determined by beta. The only unknown one is beta, and it's a vector or real number. Is that clear for everyone, the concept of these parametric models? If there is any question, do not hesitate. Okay. So as I said, these type of models are extremely restrictive in a way. They are not very flexible. In real data, they are very unlikely to be true. And in that sense, they may not be very useful for prediction, but they are extremely easy to estimate because you can estimate them by maximum likelihood estimation. And maximum likelihood estimation has a lot of very nice properties. So if the model was correct, it would be very easy to estimate. But in practice, this model is often incorrect. So if you want to use it for prediction, it will not yield extremely good predictions. Then you can go to semi-parametric models. So semi-parametric models are models in which the distribution of the data depends on a finite dimensional parameter. So as I said, a finite dimensional parameter is like a set of real numbers, a finite set of real numbers, and an infinite dimensional parameter eta. So this eta will be, what we mean by infinite dimensional parameter is that it's a function or a distribution. So the simplest example of all is a classical linear model. So you have y is equal to x prime beta plus epsilon, where you just assume that the expectation of epsilon x is equal to 0. Then, is it clear for everyone that the distribution of y given x, so if you fix x, the distribution of y is going to depend on two things. Beta, so this is the finite dimensional parameter part, and eta, which is the distribution of epsilon given x. Is that clear for everyone? If you fix x, because of this formula, the distribution of y will depend on beta and the distribution of epsilon given x. So this is a bit more flexible. Like, there is one, in a sense, there is one part that we don't restrict at all, is the distribution of epsilon given x. This we don't restrict at all, but in a sense, the effect of x is still assumed to be linear, so this is the part that we restrict here. That is the part that is parametric, it's this linear part. And so what is nice with this kind of model is that it's more flexible than the exact parametric models, but it's still relatively easy to estimate because you can just do OLS. Okay, so that's the advantage of the semi-parametric models, is that they will be relatively easy to estimate while being less restrictive than parametric models. So, and you can use that to form predictions. Is everything clear for the semi-parametric models? Okay. Yeah. And then you have the most general type of models, which are the ones we are going to study in this part of the course, which are non-parametric models. So non-parametric models, the simplest one is to think of the conditional expectation. So if you have a variable y and a variable x, you can always write y is equal to g of x for some function g, and plus some epsilon. And here, g of x is just the expectation of y given x. So that's the average value of y when x is equal to this value of x. And your epsilon is just y minus gx, g of x. And you can verify that once you use these definitions, you indeed get that the expectation of epsilon given x is just the expectation of y minus the expectation, of y minus g of x. So this is just the expectation of y minus the expectation of y given x. And so if you develop the expectation, you get this. And this is the expectation of something that is constant when your condition on x. This is just the expectation of y given x. This is the mathematical part for you, but you don't necessarily have to understand it. But the idea is the following: if you have y, so let's say prices, you can always write y as the average value of y for the x corresponding to your observation plus an error term, and this error term will be mean zero once you fix x. Okay? So essentially, think of it as in a class. If I have a class, I have grades in a class. For any student, I can write his grade as the average grade in a class plus an error term, right? Which is just the difference between his true grade and the average grade, and this error term will be mean zero. On average, over the student, it will have a mean of 0. This is exactly the same idea here. So what we call non-parametric models is essentially models where the distribution of the data is not restricted at all. Does not only depends on infinite dimensional parameter. Here, when I'm writing that, as I said, I'm never putting any restriction, right? Because I just say g of x is this, epsilon is this, and then I will always be able to write that. These are models which are completely unrestricted. Is that clear for everyone or not? Do not hesitate if there is any question or any. And is it clear for everyone why this construction gives you that the average of epsilon given x is equal to 0? Really think of it as, I think again the best example is grade in a class. So let's say x is just a class indicator. I have different, in high school, I have different classes. So x is just the class indicator. X equal 1 is class 1, x equal 2 is class 3, and it goes on. And y is just grades. Okay? That just tells me I can write the grade of an individual as the average grade in its class plus an error term, and this error term will be on average 0 in his class or their class. Clear for everyone or not? Or should I give if it's not clear, I can give more explanation.
In the second line.
Yes.
The previous one.
This one.
Yes. Why there is no deconditional tweaks?
Because it's my fault because I forgot it.
Sorry,
That's good. No, that's good. I make mistake when writing on the board, so don't hesitate to note it. Okay.
And the conditional tweaks applies to the whole part?
Yeah, it applies to all of these. So this is you take the average of this once you have fixed x. So this is the idea of saying I fixed a value of x. So let's say I fix a class, and then I take on this class the average of y minus g of x. And in my example, g of x is just the average class, the average grade in the class I have fixed. Okay, just this writing is important, this conditional expectation writing, because a lot in this chapter and in this part of the course, I will just write models like this. Okay, I will just write y is equal to g of x plus epsilon. And you just need to understand that this g of x is a conditional expectation. And this is not an assumption in a sense. This is just I can always write this. So it'd be the same thing as I can always write a linear model, and because there will always be a best fitting linear line. There is always a conditional expectation, which is actually the best prediction you can think of in some sense. Okay. So what are the pros and cons of this model? So the pros is that g of x is always a better prediction than x prime beta, because in a sense it's a more flexible prediction, right? Like if you just take a linear form, it's less flexible. If the true conditional expectation of the data is not linear, then you're just approximating it by a linear form, so you're less flexible. The cons, of course, as I said, is that g of x is harder to estimate than x prime beta or beta itself. It's harder to estimate the conditional expectation than to estimate the best fitting line. Simply because the conditional expectation can be any function, while the best fitting line is just a line. So it's more restricted. It's limited to linear function. Now, the point is when you have big data and you have a large number of observations and not too many variables, because if you have too many variables, you run into problems, you can have hope to estimate G precisely. Okay, if I take again my examples of flats, okay, if I have a data set with 100 flats, it's going to be very hard for me to estimate the average value, the average price, precisely the average price of a flat which is 100 square meters, EPCB and built in 1990. Now, if I have a data set with 50,000 flats, that's much easier, right? That's essentially what I'm trying to say here. So you could tell me, and there will be some truth to it, is in the first chapter, in the second part, we talked a lot about this idea of adding nonlinear term to a linear model to approximate more general functions, to allow for nonlinearity. And actually, you can essentially use this trick to estimate a non-parametric model. So what you could do is, if x was univariate, for instance, to estimate the conditional expectation, so to estimate G in this model, you could just run y on an OLS regression of y on 1 x squared until xp for some p. Okay? And essentially, this will approximate g. And then I have a resulting prediction that should approximate well g. So if what you should understand is that if g can be written as a polynomial of degree at most p, then this will exactly estimate g. If g cannot be written as a polynomial of degree at most p, then this will just be an approximation of g. Okay? But as the more I increase p, the more I will approximate g well. But the more I increase p, the more I have variable in my OLS regression, and the harder it is to estimate these beta coefficients. So again, there is a trade-off here. If I do this thing, one difficult question is how do I choose p? Because if I increase p, I'm going to get less bias because I'm going to approximate the g better and better. But it's going to be harder to estimate the beta coefficients because there are more of them, and I get more variance. And so this idea is called series estimation. And as we discussed also in part 2, yeah, if I want to increase p a lot because I want to approximate g much better, but the issue is this creates variance. So one solution would be to use the lasso, and that's what we did in part 2. But the limit of this solution is sparsity. The limit of the solution is that the lasso relies on sparsity, so the lasso allows you to put a very large p here, and if you replace OLS by lasso, you can put a very large p, but that will only work if the g is well approximated by a sparse combination of the covariates in that case. So if it's well approximated by a polynomial of this form, but with only very few non-zero coefficients, which is also limiting. And another remark is that you can use other functions of x rather than x to the power g. Here I just use x to the power g, but you could consider many other function of x, transformation of x that you put in a linear regression. So is this somewhat clear for everyone? This idea that you could approximate g as much as you want by adding nonlinear terms in your linear regression, but really the tension is the more you add term, the more you get variance. One solution is a lasso, but as we saw, the limit of the solution is sparsity. So if you don't believe in sparsity in that case, you may not want to use it. And so there is this standard technique, which is a series estimation, which is just you add terms and you estimate by OLS, not by lasso. But then the main difficulty is that then P must be chosen in a way where you balance bias and variance. So where you balance the flexibility of the model you're actually estimating and the variance it creates to estimate such a flexible model. Any question on this? Don't hesitate. Huh? Okay, so this is one example. So let's say you have a data set and you want to predict wage as a function of age in the data. The dots are the data points. And this is what happens if you run a regression of wage on a constant age to the square, h to the power 3, and h to the power 4. That's what is written here, degree 4 polynomial of wage as a function of age. Then you see that you get some kind of nonlinear function. Okay? Now, if you were to increase, what you can see is that if you were probably to increase p, so to increase the degree of the polynomial, actually probably in the middle your function would go higher, because you see that here you have all those points which are very high. But your function will also be less well estimated. So really the idea is very similar as saying, you know, like the standard thing would just be to say, there is a true curve, which is a conditional expectation. I could approximate it by a line. That's what standard OLS does. Or I can approximate it by a polynomial of degree 2 or a polynomial of degree 3, and it goes on. So I can increase the degree of these polynomials, and I will get a better approximation, but more estimation variance. So and this is up to now. This is what we did last time. Are there any questions on this? Is it clear? Okay. So if you want further reading on non-parametric regression, you can check this book, which is on Toledo in the library, and in particular, chapter 7. So the rest of this chapter will be about moving away from this idea of series estimation and discussing machine learning methods for estimating the conditional expectation. Okay, so and this machine learning method will be decision trees on random forests, which are linked to each other, and neural networks. So what you will, what is important as well is, so decision tree on random forest we will really use in the further chapters. Neural network, I just talk about it in this chapter, but it will not be at the exam. That's for, let's say, general culture. I don't use it so much. The reason why is there is, well, first it's more complex, let's say, and second, there is a lot of evidence that for, say, I would say as a general sense, social science data, meaning also economics and most of business data, which is like data on human behavior, random forest typically works much better than neural networks. So neural networks can be very good for things like language, as you know, with large language models and these kind of things, but it's not so good for social science data. That's what most of the evidence says. Okay, so in that course I focus on decision tree and random forest, but I will give you a quick introduction to neural network for general culture, but this is not at the exam. I don't expect you to know and understand that for the exam. Okay. So let's start with decision tree and random forest. So the discussion in this chapter is really based in this subsection of this chapter is based on chapter 8 of this book, and all the figures come from this book. So for random forest, it's an excellent book. We also use it for the exercise in the next lab session as well. So if you want further reading, I really encourage you to have a look at chapter 8. Okay. So decision tree and random forest are a different way to estimate a non-parametric regression, or to estimate the conditional expectation. And I think the best way to understand it is to look at this. So in the chapter of the book, what they consider is the following task: is I want to predict the salary of a baseball player as a function of the variable hits, which is the number of hits that the baseball player had in the previous season, and the number of years of experience of the baseball player. So here you see actually data points for the baseball player, which are, and they are represented in terms of the value of years for this baseball player and the number of hits of this baseball player. Okay? And in your data, you observe a third variable, which is their salary. And I want to predict the salary as a function of hits and years. Is the task clear for everyone? What the task is that they discuss? Okay. So essentially the idea of decision tree is to say, I'm going to take my covariate space. This is my covariate space. My covariates are hits and years, so I can represent it on a plan in 2 dimensions, and I can represent it like that. And I'm going to partition my covariate space in rectangles. We will explain later how you come up with these rectangles, but you partition it through rectangles, you get some rectangles. And the idea is to say, if I'm given a new value of x and I want a prediction for this new value of x, so say I'm given a player with 20 years of experience and 200 hits. So it's gonna be this player is gonna be somewhere here. If you can all see on the screen. Then I'm gonna say my prediction of this of this player is just the average salary of the data points which are in the same rectangle. So I'm gonna take this is the rectangle R3 is the rectangle in which my player is. I'm gonna take all the data points which are in R3, so all these yellow points within R3. I'm gonna average their salary, and that will be my prediction. So in a different way, what I'm doing is I'm saying I'm predicting y as the average over data points, and these data points are the data points which are in the same rectangle. And why in the same rectangle? Because you want to use data points which have similar x. Okay, so among the three rectangles, R3 is definitely the one made of data points which are the closer in terms of x to my new observation. And that's why I use R3. That's, if you come back to my example of flats, that also makes sense. Of course, in my data, I may not have exactly a flat which is like your flats. Meaning, if you remember, your flat has 100 square meters, EPCB, and is built in 1990. I may not have exactly that my data set. But what I can do is just say, my prediction will be the average price of flats which have similar x. So meaning I could take flats built between 1980 and 2000 with EPC between C and A and with between 80 and 120 square meters, for instance. Okay, that seems a very natural way to go. And that's essentially what this is doing, right? I'm finding rectangles of values of x which are close to my new x that I want to predict. And I use the data in this rectangle and average them. And here you have a kind of similar tension as before. On the one hand, I would like to make the rectangles as small as possible, right? Because if I have big rectangles, large rectangles, what happens is I'm gonna use the data points which have very different x from mine. So they might not be a good, let's say, benchmark for my own x. You might say, so I have this rectangle. I want to predict this point, you remember? You might say that this point here is too far away. I should not use it. I would prefer to use a rectangle which is this, much smaller. So you might want to do that, but there is a tension again here. Is if I do that, if I make a smaller rectangle, I'm going to average less data points. So I'm going to have more variance. So that's always the same issue here is if you make smaller rectangles, you're going to reduce your bias because you're going to use data points which are more similar to your new x, let's say, to your new observation. But you're also going to use less data points. So you're going to increase your variance. So here you have very similarly to this series estimation, you have again this trade-off. I want to make smaller rectangles, and here smaller rectangles is very similar to adding more polynomials. But the cost of this is that I increase my variance in both cases. So all the question is, how do you optimize the rectangles? How do you find rectangles that solve this trade-off in a good way? And all that this machine learning technique do, like decision trees, random forest, is finding ways, computationally attractive ways to solve this trade-off. sorry, I'm just okay. Okay, is it clear for everyone? So now we can discuss all how the rectangles are determined. So as I said, the main idea of decision tree is I partition the feature space. You remember, feature means covariates in machine learning. So the covariate space with respect to some covariates. And the partition are always through high-dimensional rectangles, also called boxes. So I say here high-dimensional rectangles because when I have two variables in X, these are really rectangles. But when I go to dimension 3, these are boxes. And then when I go to dimension 4, I mean, we don't have a human term for it. Okay, but these are just, if you increase the number of covariates, these are like higher dimensional versions of rectangles. And then the prediction of y for a subject with filter x is the average of yi for observation in the training data, such that xi and x, such that xi, here there is a typo, xi is in the same box as x. I should have removed the and x. We'll correct it. And a decision tree, you can represent it in different manners. One is you look at the covariate space and you represent these different rectangles, but of course this only works in dimension 2. Or another one is really like a tree, like this. So the tree starts where, so as I said, I want to predict baseball player log salary as a function of years of experience and hits during last season. First, so the tree essentially is splitting the covariate space. Here first, I split between two branches. One is when years are lower than 4.5, and the other one is when years are larger than 4.5. And then I split the data again into the cases where hits is lower than 117.5 and the cases where it's larger than this. So essentially the first split in the tree is the one that splits the part which is left to this line with the part which is to the right of that line. Okay, so it decides if years are lower than 4.5 or larger than 4.5. And then afterwards, I take the data where years are larger than 4.5 and I split between hits smaller than 117.5 or larger than this. That's what I do. So I take, this corresponds to what is higher than this line or lower than this line. So first, what is important is that decision trees will always consider partitions which can be represented like this. Partition in rectangle which can be represented like this. So I decide on a variable, let's say year. Then I partition the space with respect of some threshold with respect to year. And then I consider separately the two rectangles are created, and I subdivide these two rectangles and I go on. Is that clear for everyone? And what you see here, like at the bottom of the tree, is actually the average in the corresponding rectangle. So this 5.11 corresponds to the average for observation which have years lower than 4.5. So it's the average of salary in R1, in the rectangle R1. Here the 6, you can see that this is the average salary for observations which have years larger than 4.5, sorry, and hits lower than 117.5. To the left, you are lower. To the right, you are larger. So this is the average salary in R2. Okay, and 6.74 is the average salary in R3. Is that clear for everyone? So what you can actually see also, I mean, this makes a lot of sense, but what you can actually see is that when players have more experience, their salary is higher, right? Because when years is lower than 4.5, you have only a salary of 5.11 on average, Otherwise, the salary becomes larger. And when they have more hits in the last season, the salary is also higher, which also makes sense. This is what we would expect. So is this construction with the tree clear to everyone? Okay. So some vocabulary on these trees. So the region of the partition, so what I mean by that is that the rectangle in the end, they are called terminal nodes or leaves, because this region, they just correspond to the end here of the tree. So if you think of it as a tree, the end of the branches are just leaves. So they are called terminal nodes or leaves. The points along the tree where the predictor space is split are internal nodes. So here, this is an internal node, and this is an internal node. And then the segment of the tree that connects the different nodes, so let's say this segment, are called branches. Okay, so this is, if I might say, pretty human language. Is this clear for everyone, this vocabulary? So the general steps, but this is really a repetition. So you divide the predictor space. This is the set of possible value for x1 till xp. So you have p covariates into j distinct and non-overlapping regions, r1 till rj. In our example here, j is equal to 3. And then for every observation that falls in rj, we make the same prediction, which is simply the mean of the response value for the training observation in rj. Okay, this is just a summary. Now, I still haven't answered the main question, which is how do we decide on the partition? So how do we build the tree? That's what we are going to discuss. So to build the tree, we are going to do some kind of recursive approach where we do subsequent splits, right? And that's exactly what you see here. You do subsequent splits. So the idea is just the following. So when you are at a point in the tree, so say here to begin with, but it can also be here. You're going to choose one covariable with respect to which to split. That's what we see. It's time you choose one covariable and a threshold S with respect to which we split, such that the sum of the square prediction error after the split is minimized. So what does that mean here? A split is determined by a covariable and a threshold, okay? There are an infinitely many of these splits, right? Because the threshold can be continuous. And each of these splits is going to divide one rectangle into two rectangles. For each of these two new rectangles, I'm going to have a prediction, which is the average y in this rectangle. Is that clear for everyone? For instance, I consider the rectangle, which is the union of R2 and R3. That was that. I want to decide where I'm going to split, if I'm going to split and where I'm going to split. If I consider this split, for every observation in R3, I get a prediction which is the average y in R3. For every observation in R2, I get a prediction which is the average y in R2. For each of these predictions, I can compute the prediction error. I can square it and sum it. A bit like OLS. You remember OLS is summing squares of prediction errors. That's very similar. And that's exactly what's happening here. So for a given covariable j and a threshold s, I can define two rectangles, which are one is the x such that xj is lower than s, and the other one is the x such that hj is greater than x. And then in these new two rectangles, y star 1 is a mean is a prediction, so it's a mean response for the training observation in R1, whereas y at R2 is a mean response for the observation in R2. I can compute for every y in R1 the prediction error, square it, sum it, and I do the same here. Okay, so in a sense, each of these possible splits is creating predictions. Each of these predictions creates prediction errors. I'm gonna, for each possible split, I look at the prediction error and the sum of square prediction errors that this split will create, and I'm gonna pick the split that minimizes the sum of square prediction errors. It's quite similar to OLS, where I pick the line that minimizes the sum of square prediction errors. Here, I pick the split that minimizes this. In practice, there are computational ways to do that simply, of course, because one difficulty is that you have infinitely many possible splits. Like for OLS, you have infinitely many lines, but people have, I don't go into details here, but people have computational way to do that simply, to pick the optimal split in that sense. Okay? But is the rule clear for everyone? Yes? Or is there any question? Okay. So as I said, solving the best split at each step can be done quickly as long as you don't have too many features. If you have too many features, it starts to become complex. And what you should note here is that rather than directly finding the overall best partition, we are finding the best partition at its split. In a sense, we are myopic. We look at what one split will do. We don't look 2 steps ahead. Okay? Because maybe if you were to look 2 steps ahead, you could do something better. Here we just do, at every split, at every node, we just look at what is optimal now. Okay? We don't consider sequences of split directly when we optimize. We just do one split by one split. Is that clear for everyone? And this is called a greedy algorithm. So it's an algorithm where at every step you do what is optimal, and you hope that this is optimal in general after the sequence of steps. And machine learning is based on this construction a lot, and it works very well in practice. Okay, so the issue is that optimizing every steps at the same time is too complex computationally. It's much simpler to optimize steps one by one, and then hope that this is good. And in a way, we humans work very similarly. You don't necessarily try to optimize for what will happen to you in 20 years or 25 years. To some extent you do, but most of the things you do are about what will happen in the next few years. Yes?
Maybe it's trivial, but do you first fix the variable and then look at every possible threshold, then go to the next variable, optimizing that way, step by step, or?
Yes, well, the thing is that at each step you still trial every possible variables. But what I mean is that in a sense, the criterion that you use to choose the best split is just based on what this split does now. It's not based on what I could achieve by further dividing after this split. Do you see what I mean? I'm not looking 2 steps ahead, because afterwards I'm again gonna split, and maybe I could realize that once I'm again split, my original split was not optimal, because if I had done another split, I could split better afterwards. It's a bit complex to explain, but I'm not directly saying, in a sense you can see it in the following way. I'm not directly looking at all possible partitions in rectangles and saying this is the optimal one. That's not what I'm doing, right? I'm doing something one step by one step, and that's because looking at all possible partitions is too complex. It's too computationally complex, so I rather do this thing where I construct my partition where at every step I try to do something optimal. Is that a bit clearer? Yes.
So if we have one covariable that, for instance, has much more variability than the others, is it possible that we divide the same covariable in the first step, for instance, and then also the second, the same one in the second?
Yes, it is possible, and that's actually a very nice. So the decision trees, that's exactly what they do. And the problem is that this can happen, as you say, but this can create a lot of overfitting. So when we move to random forest, there are some fixes where you actually randomized you randomize the set on variables on which you are able to split to avoid that this kind of problems happen, to avoid that you always split on the same variable. Because otherwise, if you always split on the same variable, you risk overfitting. Is that does that answer your question? Yeah. But with decision trees, this is allowed with decision tree. At this point, this is allowed. But it's indeed a problem, and that's why people go to random forest or more complex things. So very good remark. Okay, so what I propose now is that we have a break until 10:05, and we start again. Hi. So we meet afterwards? Or? Yeah. Okay, perfect. We can go to my office. Let's start again. Okay, so let's advance a little bit. So another question is, when do we stop? When do we stop splitting? I told you always split, but I didn't tell you when do we stop. So in general, you choose a minimum number of observations. Standard rules are either 1 or 5. And then you split until every region has fewer than fewer than this minimum of observations. But of course, so you're going to split many times. You have a minimum number of observation. If a region has lower than this minimum number of observation, you stop splitting. That's what happens. You stop splitting this region. But in the end, you're going to end up with a tree which may create overfitting for 2 reasons. The first one is that you're going to get very small rectangles, right? Because if you choose a minimum number of observation equal to 5, you're going to get like very small rectangles. You might get a lot of variance. And on top of that, you will notice that up to now to choose and everything, we have only used the training data. So you remember that in machine learning there is all this trick and this idea, which is to say, if you want to avoid overfitting, you need to do a train test approach. And up to now, we have only used the train test. So only the training data, so we might create overfitting. Okay? So overfitting can come from two things. First, that the rectangles are very small, and second, that we only use the training data. To prevent overfitting, we go one step further, and we prune the tree. So by pruning, I mean pruning is I take out leaves from the tree. And this process of pruning these trees that we created is what prevents overfitting. And that's where we are going to use a test set. So essentially, once you have completed this process of doing every split until every rectangle has a minimum size, you get a big tree, like this. Okay, so this is the data, the haters data, so the baseball data. And you get such a tree. Now what we are going to do is pruning, so we are going to remove some branches. By this we mean we are going to remerge some rectangles together to prevent overfitting. So how do we do that? We first start by determining a sequence of subtrees. So, like if you want to prune these trees, there are many ways to prune this tree, right? I could start with this leaf, then do this one, then this one, or start with this one, then do this one. I mean, there are many ways to prune, and trying all of them is too computationally costly. So first, we are going to restrict ourselves to some interesting sequence of subtrees. So when you prune your tree, you get a subtree. You get a tree which is contained in the original tree. And we are going to select a sequence of subtrees. And so you do what we call cost complexity pruning. So let's say that T0 is the big tree, the tree split until each region has fewer than a minimum number of observations. So it's this tree. Then what I'm going to do is that I'm going to go up through this tree and get a sequence of subtrees. How do I determine them? I take some alpha and I will vary alpha from 0 to infinity. And for every alpha, I'm going to determine the subtree that minimizes this. So this is just the prediction error of the subtree. Okay, so I can consider many subtrees. This is the sum of the square prediction error of the subtree. And here I have a penalty term. This penalty term is alpha times the number of leaves, the number of final rectangles in a subtree. When alpha is equal to 0, then the T that is selected by this is going to be T0, right? It's going to be the big tree. When alpha is equal to 0, the big tree is the one that minimizes the prediction error in the sample. That's logical, right? Because the rectangles are smaller. So the smaller they are, the more I'm going to minimize my prediction error in the sample. Now, when I grow alpha, I pay a price for trees with many leaves. So as alpha will grow, the solution to this will not be the original tree, but it will be a subtree of the original tree, an exact subtree of it. When alpha gets to infinity, I will get to the ultimate case where I have no tree anymore. whereas the optimal subtree is actually the tree which is not partitioned at all, right? Because I pay so much cost for every leaves that I have, every terminal node, that I don't want to pay any cost. That's quite similar to the lasso. You remember the lasso, we have a penalty. When the penalty was 0, the lambda of the lasso was 0, we get OLS, essentially. But when the lambda was infinity, you get all coefficients equal to 0. Here, when alpha is equal to 0, you get the original tree. As you increase alpha, you get trees, subtrees of the original tree, which are less and less complex, which have less and less leaves. And as alpha goes to infinity, you just go up fully on the tree, and you just get like no tree in the sense that you have no partition anymore. The best subtree is the trees that correspond to no partition, where I have removed all the leaves. And so what's interesting here is that people have some algorithm to do that, and you can to choose the sequence of tree for alpha as a function of alpha. You have a finite, it will change as a function of alpha in a discrete way. So for some interval of alpha, you have the same trees that solve it. And what's interesting is that these are the trees that we solve this alpha, they are the subtrees, they will always be contained in each other. In a sense that you're gonna increase, so say you're gonna increase alpha, when you increase alpha, you first remove, let's say, this leaf. Then you continue, you will keep the new tree with this leaf removed, and you will remove another leaf. And it goes on and it goes on. Okay, so what I mean by that is that this sequence is actually, and this is not obvious ex ante, when you increase alpha, this sequence of subtrees is really one of trees which are contained in each other. Okay, because you could imagine, for instance, that, you know, like alpha is small, you remove this leaf, but while you continue to increase alpha, there is a point where you're better off having this leaf back and removing this leaf and this one as well. This does not happen. It's one after each other in practice. Is that somewhat clear for everyone or not? Or should I repeat? No? Yes? I should. Okay. So I will anyway just re-say it. What happened is that the sequence of trees that is determined by alpha, these are just trees which are contained in each other. So to go through this sequence of trees, I can just remove one leaf, then remove another leaf, then remove another leaf. I don't need to say, I remove one leaf, and now that my alpha is larger, I have to put back this leaf and remove two others. That doesn't happen. That's not obvious ex ante, but you can show mathematically that this doesn't happen. But this thing is just a way to determine a smaller sequence of subtrees through which to choose. Okay, because otherwise I could look at all subtrees. Here I just choose one sequence of subtrees, and that's the one I will look at. And then the question is just, to get my final tree, I just need to choose alpha. So I just choose one of the subtrees in this sequence. And then to choose this alpha, we do exactly like lasso, we use cross-validation. You remember, for lasso, we use cross-validation to choose the lambda. Here we use cross-validation to choose the alpha. So cross-validation is just, you remember, for the simplest example is I have all my data. So this is my data from I is equal 1 to n. When I do two-fold cross-validation, I divide it in two. I first train the model on this part of the data. So meaning to make my prediction with my rectangle, I average the observation in the rectangle on this part of the data. And I use it to predict here, and I look at the prediction error. I do the same while inverting the two folds. So I redo this, but where I take the average on this part of the data to give me the prediction for each rectangle. And then I look at the prediction error here. And I take the average of the two prediction errors. And I take the alpha that minimizes this. Is that clear for everyone? Did you have a question on the...
Yeah, I was by one node each time.
You reduce by what? So what you can show is that when alpha increases, each time the subtree changes, you're just removing one node.
Okay. So maybe one on the right, one on the left.
Exactly.
Not at the same time. Okay.
Yeah, you can show that it will be only one each time.
Okay.
You can show that. Is this clear, this cross-validation? The simplest approach, but would be just sample splitting. I divide the data in two. I have a train test that I use to compute the average for each rectangle. These are my prediction. And then I look at the prediction error, and I take the alpha that minimizes this. Now to be more efficient, we do that while reversing the role of the train on the test. And we average over the two. Clear for everyone, the cross-validation? Or yeah? Good. Let's go. Okay, so this is the general algorithm that is just summarizing everything I said. So first you do this split, like this recursive splitting, to grow a large tree. Then you use this coarse complexity pruning, meaning you find the sequence of the tree as a function of alpha. And then you use cross-validation to choose alpha. So you divide the observation into k-fold. This was a two-fold case. Then you repeat step 1 and 2 on all but the k-fold of the training data. You evaluate the mean square prediction on the data. And you average the result for each alpha and pick alpha to minimize the average error. And then you return to the subtree. And you use this chosen value of alpha at step 3 in this subtree to determine your final tree. Okay? That clear for everyone? And that's very similar to, that's exactly the same that we do to choose the lambda of the lasso. Okay, and this is an example on this ethers data. So here you will see the following. So here you have the mean squared error, so that's the performance of a tree. And here you have the tree size. So the tree size is essentially equivalent to alpha. So you look at trees that grow as a function of your alpha. And what you see here is, so you will see different errors. So what they did is first they divided their data on a train on a test. In black, this is the performance in the training data. So as I said, and that's very logical, the larger the tree, the best you do on the training data. That's the same with OLS. The more you have variables, the better you do on fitting the training data. In the limit, you fit it perfectly. Here you have the test. And in the test, you see that you first get a better performance, but then the performance becomes a bit worse afterwards. Which is logical because, as we said, when the tree size is too large, you get some overfitting. And then you have the cross-validated. So this is what happens when you look at the cross-validation criterion for the tree, and you really see that the optimal alpha that you get will be 3. The one that minimizes the cross-validation criterion, so the one that this is the criterion that comes from this step 3, you see that it's minimal at 3, so you're going to choose a tree size of step 3. And you see that this gives you a better performance on the test set actually than choosing 4, 5, 6, and it goes on. So what's really interesting here is that you should really see the overfitting, because you see that you get worse. You get better for the training set, but then when you increase the tree size, but at some point when you increase the tree size, you get worse on the test set. Yes?
Does cross-validation include the training and the test, or is another procedure?
in general, you don't have to do a training on a test, but this is for a pedagogical purpose to show that when you use the cross-validated rule to choose, you do better on the test than if you pick, let's say, this one or this one or this one. But in practice, you don't need to do a train on a test. I mean, you do it when on the cross-validation step, but you don't need to divide at the beginning for train on test. This is just pedagogical here. Is that clear? Okay. So now let's just discuss what are the advantages and disadvantages of trees. So the first one is that it's super easy to explain and interpret. I think that's something that we can explain to maybe a 5-year-old kid. It's also good to handle categorical predictors because you can just split along categories. But in practice, it doesn't work so well, and it's not very robust to outliers and this kind of thing. So actually, even the main problem of the trees is that they have large, in practice, if you use that, they still have large variance. So, you know, like we use this cross-validation to minimize, to avoid the large variance on the overfitting. But what people find in practice is that this is not enough. This doesn't work perfectly. So people came up with new ideas that built on these decision trees and that allow to reduce the variance further, to prevent overfitting further. These new ideas are called bagging and random forest, and they are based on the following principle. You know that when you average many uncorrelated observations, you reduce variance, right? The variance of the average of data of some data on 100 Belgians is much higher than the average of the same data over 1,000. Okay, that is like averaging uncorrelated observations allows you to reduce variance. So the idea of bagging on random forest is just to say, okay, we are going to build trees. We are going to try to make those trees be uncorrelated with each other, and we are going to average their prediction. Each of them gives me a prediction, each of these decision tree. I'm going to try to make them uncorrelated with each other, and then I average the prediction. All the question is, how do we make trees quite uncorrelated with each other? And that's what bagging and random forest do. So this is the principle. So let's start with bagging. So bagging is just a nickname or a smaller version of bootstrap aggregating. So bootstrap is actually a principle where you take your original sample and you draw a new sample from your original sample. So what you will do is that you will draw observations, new samples of an observation from your original sample. So you have a first sample. Your first sample is, let's say, your original sample in your data is, let's say, I should do it like that. It's these 5 data points. I'm going to construct new samples that I call bootstrap sample. And what I do is that these samples are going to have, for instance, the same size as this one. But to determine their observation, well, what I do is that for the first observation, I will choose randomly one of these 5. For the second observation, I will do the same. I choose randomly one of these 5. The third, I do the same. The fourth, I do the same. The fifth, I do the same. And this is what we call draw with replacement, because for the first observation, I choose just randomly one of the 5. Then the second, I do the same. And it's with replacement because I don't say, okay, for the first, I have chosen, let's say, this observation. I remove it afterwards. I can't use it anymore. So you can have you can have several times the same of the original observation in this new sample. But the idea is I'm constructing new samples from my original sample, but these new samples, they don't always have the same observations in it, right? Because I could have a sample, when I repeat this process many times, I'm going to have a sample where I could have 3 times this observation, 1 time this one, 1 time this one. And then another sample where I have 2 times this observation, 2 times this observation, and 1 time this one. Okay, there are many different possibilities. So I do that b times. I create b new samples of n observations. And what's interesting is that these different samples, as I said, okay, they come from the same original sample, but they have different observations. So you create some degree of independence between the new samples, some degree of uncorrelatedness. And then on each of these B samples, you can train a tree, a decision tree as we saw, and then average. Each of these decision tree, this decision tree gives you a prediction, and then you just average the predictions. And the idea is this decision tree will have some degree of uncorrelatedness because they come from different bootstrap samples. And thanks to that, that will reduce the variance when I average. Because you remember that when you average things which are somewhat uncorrelated, you reduce variance. What's also interesting is that in practice, people find that you don't even need to prune these trees. You can grow them, take them like this big tree before you pruned, and then average, and that will reduce the variance sufficiently. You don't need to go further. You don't need to do the coarse complexity pruning on the cross-validation. The only thing where you might do cross-validation is you don't prune trees, but you still have this minimum number of observations in each terminal node, and for this one, you could select it by cross-validation, okay? By trying different ones and seeing the ones that perform the best in a cross-validation. Is that clear for everyone? So this is the first way to make uncorrelated trees and then average them. No question. So then your colleague made a very good point earlier, is that if you have one predictor, which is a very strong predictor, it might be that regardless of the sample you create like this, you always split on this predictor first. And this can create overfitting, and this somewhat creates some kind of degree of correlation between the different trees that you have. So to perform even better than bagging, people use instead random forest that avoid this kind of problem that you might always split on the same covariate, on the same predictor. And makes trees which are even more uncorrelated. So the idea of random forest is as follows. You do essentially like bagging, so you generate these different bootstrap samples on which each of them you're going to train a tree. But on top of that, at each split that you do on any of these trees, you are going to randomly select small m out of the p different possible predictors and force yourself to only split on one of these m predictors. So this avoids that you always split on the same predictor, because there will be splits where this predictor is not in the m out of p, and you avoid to do that. You avoid to split on this predictor. And the rest of the process is exactly the same. The only thing that changes is that at each split, you restrict yourself to some predictor. So you forced that there is some variation in the predictors on which you split. And in that way, you uncorrelate trees further. Yes? Yeah, it's just random. It's really fully random. You select M randomly out of. And so one question is just, so you can, how do you choose M? So you can choose M by some cross-validation, but there are also some rule of thumb. And so when you want to do classification, so meaning classification is when your variable is binary, your y is binary, and you just want to decide is y equal to 0 or 1. Then typically what works well in practice is M of the order of square root of p. And when you just, your variable is continuous, so for regression, when your y is say a wage, like it's a continuous variable, not a binary one, what works well is M of the order p over 3. And so the idea here is just that this decorrelates the trees even more. Bagging decorrelates through using different data for each tree. And random forest decorrelates further by adding to that we use different variables for each split. And this is just an example. So here you see, so this is not the ethers data. This is a class. I think it's a classification problem. Yeah, that is a classification problem in kind of genes. So you have genes of patients, and you want to predict if they have a disease or not. So your Y is just an indicator for having a disease. And this is the so you divide your data in a train and a test. This is the performance of random forest as a function of the number of trees that you create and then average. And for different values of M. So the yellow one is M is equal to P. So when M is equal to P, you are just back to bagging because you always, you can select any variable at every split. Then you have M is equal to P over 2. You see that it's almost the same performance as yellow. And then you have M is equal to square root of P, which is the green one. And you see that it's clearly the best. As we said for classification, that the rule of thumb is to say M is equal to square root of P works best. But here you really see that the green improves on the yellow. So the yellow is bagging. But here you improve on bagging by taking the green one. And what you also see is that at a point, there is a point where this stabilizes, where increasing the number of trees does not change the result, does not change much the prediction. That is the same with an average. When at some point, you know, like if you collect data on Belgians and you want to know the average wage, okay, when you have 100 data points, you might change a bit by adding more data points. When you are already at 1,000, it stops. The average stops changing much. So that's also what we see here. Yes, and then
doing the bootstrap resampling, that doesn't change for the random forest.
Yeah, you still do the bootstrap resampling. So the data is still through the bootstrap resampling. Yes?
So why do we choose a different number of those covariates for classification and for regression?
That's a good question. So this is more of a problem with it's kind of data specific, but the reason why you might want to choose, let's say what I can give you as an example. So these are rule of thumbs. They don't always work often. Why do we choose lower number, let's say, for classification? Is because classification, in a sense, it's much easier to fit perfectly a 0-1 data than to fit a continuous data. So in a sense, overfitting is more serious for classification than for regression, so for the when you want to predict a continuous variable. And for this reason, you need to decorrelate even more for classification. So that's why you take an M, which is, I mean, the rule of thumb says square root of P rather than P over 3 for this. Now, this rule of thumb is just based on what works well on many data sets, it doesn't work well always. But yeah, at least I hope what's interesting to know is that, in a sense, overfitting is more prevalent for classification than for regression because of the number of degrees of freedom that you have. It's easier to fit a 0, 1 than perfectly than to fit a continuous perfectly. So that's why you need to protect yourself against overfitting more at classification. I hope this answer, but the precise value, I mean, this is just like, I would not take it as at face value as this is just like people have been experimenting and it looks like this works well in many cases, but there is not much more to it. There is no theory behind it, let's say. Is there any other question on this? Okay. So now we can discuss neural networks. So neural networks are another way to do this non-parametric regression. And essentially, they are based on an architecture which is supposed, and I really say supposed, somewhat to mimic the way neurons work in the human brain. There are still many differences. And a very complex evolution of this architecture is what is behind large language models. But it's still it looks very different from what I have here, but because it's a very complex evolution of it. But the idea is, I want to predict I want to predict y from x. The simplest version of the neural network is the following. How do I generate my prediction? I have 3 covariables, x1, x2, x3. I'm going to give a weight to each of these 3 variables. So, and then these 3 variables with these different weights, W1, W3, W2, they will enter a neuron. So this is called a neuron. And the neuron will be influenced by these weighted variables plus some bias term B. And then it will output something. And this something is a function of B, the weights on the original variables. And typically, this something is just a function f. Usually the function f is just this function, the ReLU functions that we call f of x is equal to the max of 0x. So that's just a function which is 0 when x is negative, and then just equal to x. Okay? So this is 0, this is just a function like that. And so you apply this function to the weighted sum of the x that you have plus some bias term. That's the simplest architecture. So you can think of it as you have some signal that comes to your neuron. Okay, so these are inputs, these are some weights that determines how well the signal passed through the neuron. You have some bias term in the neuron and you output a new signal. Now what happens in practice is you don't have a single neuron, you have what we call a neural network. So you have a network of neurons, and so you start here. Your x, you have 2 first neurons here. Each of your x enters each of these 2 first neurons with some weight. There is some bias term. They give a signal out, and this signal out goes to the next layer of neurons. And you go on, and the signal of the last layer of neurons is your prediction. So here, for instance, in the last layer, you can have 3. If you would like to predict a 3-dimensional thing, so maybe you don't want to predict only the price of your flat, but you also want to predict who the buyer will be. Then you might have a more dimensional prediction, and so you might have more than 1 neuron at the end. And essentially, the architecture is like that. You have just layers of neurons, one after each other, and each of them inputs something for the next one. And typically you choose f. The f is the same. F is fixed. And we call intermediate layers of neurons the hidden layers. So this one is the hidden layer in that case. And the last layer is the output layer. And it has as many neurons as the dimension of y. And often you will hear this term called deep learning. That's because people use deep networks. And by deep network, we mean network with many layers. So they are very long, but each layer is relatively small compared to the length of the network. And so in machine learning, there are many things we don't understand. And now people start understanding why this deep architecture has some nice properties, but for a long time, they saw it was working well, but they did not understand very well why it was working well. And so all the thing is, so typically you fix your architecture, or you try a few different ones, and you just, when you train on your data, what you optimize is those weights on these bias terms. So you have to decide, you fix the neuron architecture, but you try to find weights and bias terms that fit the data well. And to do that, essentially, so this is your prediction of your neural network. You will have your data, and you're gonna choose the weights and the bias terms that minimize the sum of the square prediction error on the data. And actually, I mean, that should seem logical for you. This is, you can't really find, in practice, this is way too high dimensional, right? You have a long network, you have many weights, many bias terms, so you can't really find the weights on the bias that really minimize this. So you use some algorithm that tries to minimize this thing, which is called stochastic gradient descent. So if some of you have seen gradient descent, it's a stochastic version of it. And it turns out that it does a good job. And it does a good job in a way that also prevents overfitting without needing to go necessarily for cross-validation at this point. And yeah, people have troubles understanding exactly why this works so well, but this works well. Yeah, you had a question, I think, or no? Okay, so you minimize this thing. People might do some kind of cross-validation to choose the architecture of the network, but they will typically not do cross-validation to choose the W and the B, because this works without it. Because of this algorithm, apparently, of how you compute this minimizer. You can never really compute exactly this minimizer, but you can compute something that is close to it in some way. Okay. So here is further reading on this chapter. So what you should know on this chapter is really, as I said, the neural networks is not so important. That's for your own culture, I would say. What you should know is really like the decision tree and the random forest, understand how it works. Next week, you will have another lab session where you will do a bit more on chapter 3, I think, if I remember, and you will also study the random forest. And then after the holidays, we come back and I will discuss how to use the random forest for causal inference. So when you want to estimate causal effects, you will see that it's quite similar from the lasso. So we will use double machine learning, and we saw it with the lasso. We will use it there. So that's mainly it. Also, after the holidays, I will talk a bit more about the exam. There is already a mock exam online on Toledo, but I will talk a bit more about also opportunities to get feedback. Is there any last question or not? Okay. Otherwise, we can stop here. Thank you.